The central dying star is so hot that its radiation is cooking everything from the inside and producing a bubble of ionized hydrogen gas as it does. The gas bubble features cavernous shells and rings with tendrils that are expanding and destroying dust upon encounter. The star is not just glowing, it is consuming its own nebula from the inside. Radiation so intense, it ionizes hydrogen, tears apart dust grains, and expands outward in shells that push everything ahead of them like a slow-motion explosion that has been running for several thousand years and will continue for roughly 10,000 more before the nebula disperses entirely and the star is left alone in the dark. Webb utilized its near-infrared camera and mid-infrared instrument to uncover previously invisible features, including compact clumps of dust and ionized gas, providing sharper views than Hubble's 2,000 observations. The comet-shaped clumps in the main, the ones that look like streaks frozen in the outer structure of the nebula, are dense pockets of dust that manage to survive the radiation by shielding the material directly behind them. Each one is a survivor, a pocket of matter that the white dwarf's radiation could not fully reach, preserved while everything around it was destroyed. And Webb's infrared vision resolved them individually for the first time. Hubble saw the main as a blur. Webb sees each clump separately, each one a small drama of survival in the middle of a dying star's slow violence. This is what our sun will become. In about 5 billion years, when the hydrogen in its core is spent and the helium burning phase ends, it will shed its outer layers. Those layers will expand into space. A white dwarf will sit at the center, blasting the ejected material with radiation, carving it into structures. The Earth, if it still exists in any form by then, will be inside the expanding envelope long before that moment arrives. The Lion Nebula is not just a beautiful image, it is a prediction. On August 6th, just 4 days before the Lion Nebula release, Webb released a separate infrared image of part of the Carina Nebula, a massive star-forming region 7,600 light-years away. The Carina Nebula was one of Webb's first targets when science operations began in 2022, and its initial image became one of the most widely shared astronomical photographs in recent history. The new image shows a different section of the same region in greater detail, resolving individual protostars and protoplanetary structures that earlier observations could not separate from the surrounding gas and dust. The Carina Nebula is one of the largest and most active stellar nurseries within several thousand light-years of Earth, and every Webb observation of it adds detail to our picture of environments of violent competing radiation and gravity. But the images from these 2 weeks are, as striking as they are, not what has genuinely shaken the scientific community. The images are beautiful. What is shaking the community is the data behind images like these taken across 4 years of operations. Data that has been building toward a picture of the universe that does not match what the models predicted. Webb's most disruptive finding remains the existence of massive, well-structured galaxies at distances corresponding to the first few 100 million years after the Big Bang. Ultra-bright, compact galaxies blazing with intense star formation, far more luminous and massive than any theoretical model predicted could exist so early. This is the finding that has produced what researchers are now openly calling a crisis in early universe cosmology. The standard model of how the universe evolved after the Big Bang predicted that the first galaxies would be small, irregular, and relatively dim. Gravity needed time to pull matter together, stars needed time to form. Complex structure needed time to emerge from the chaos of the early universe. That was the prediction. That was what the model said Webb would find when it looked back to the first few 100 million years of cosmic history. Instead, Webb found galaxies, massive ones, bright ones, well-structured ones with features that the model said should take billions of years to develop, galaxies that, by the standard cosmological timeline, should not exist yet. Strange red dots in James Webb images left scientists puzzled for years. New research shows they are young black holes hidden inside dense clouds of gas, glowing as they devour their surroundings. Not just anomalous galaxies, but a whole class of objects that no existing model had described. Black holes in the early universe feeding so aggressively that they outshine entire galaxies around them. The models did not predict these. They are there anyway. Then, in March 2026, Webb spotted something that stopped researchers for a completely different reason. One GRB 2507002b, detected by NASA's James Webb Space Telescope and a global network of observatories, lasted an astonishing 7 hours, far longer than typical gamma-ray bursts, which usually fade in under a minute. Gamma-ray bursts are the most energetic explosions in the universe. They occur when massive stars collapse into black holes or when neutron stars merge. The burst of gamma radiation they release is so powerful it can briefly outshine an entire galaxy. They are also extremely brief. Most last under 2 seconds. Long gamma ray bursts, a separate category associated with the collapse of Massive stars typically last from a few seconds to a few minutes. 7 hours is not a long gamma ray burst by the existing classification. 7 hours is something that the existing classification system does not have a category for. The event was real. The duration was confirmed across multiple instruments at multiple observatories. And the explanation for what physical process could sustain a gamma ray burst for 7 hours when the models say the energy should dissipate in seconds is still being worked out. And then there is what Webb found at TOI 561b. Astronomers have uncovered surprising evidence of a thick atmosphere surrounding TOI 561b, a scorching, fast-orbiting rocky planet once thought too extreme to hold on to any gas. TOI 561b is one of the oldest rocky planets known, roughly 10 billion years old. It orbits its star in less than 11 hours. At that orbital distance, the temperature on its surface reaches around 2,000 degrees Celsius. Under those conditions, the standard models of atmospheric physics predicted that any atmosphere this planet might have had would have been stripped away billions of years ago by the stellar radiation. The model said it should be a bare rock. Webb looked. It is not a bare rock. It has a thick atmosphere. How it kept that atmosphere under those conditions, how it resisted 10 billion years of stellar bombardment at extreme proximity to its star, is something the existing models cannot currently explain. Separately, the Hubble constant problem has not gone away. The Hubble constant describes the rate at which the universe is expanding. Measuring it requires choosing a method. Measurements based on the early universe using the cosmic microwave background give one value. Measurements based on nearby objects using standard candles like Cepheid variable stars and type Ia supernovae give a different, consistently higher value. Webb was supposed to resolve this discrepancy by providing more precise measurements of the standard candles. Instead, Webb's observations have created a genuine crisis in early universe cosmology that ground-based telescopes never could have triggered. The data is too clean and too consistent across multiple observations to dismiss as calibration error or artifact. The discrepancy has not closed. If anything, Webb's precision has sharpened the disagreement between the two methods rather than resolving it. The universe appears to be expanding at different rates depending on how you measure it. And the most powerful telescope ever built has confirmed that the disagreement is real. What all of this adds up to is something worth sitting with for a moment. James Webb was built to answer specific questions. How did the first galaxies form? What are exoplanet atmospheres made of? What does the universe look like at its earliest observable moments? It was built to confirm, extend, and refine what we already knew. And in 4 years of operations, what it has done instead is produce a list of things that do not fit. Galaxies that should not exist, a gamma ray burst that should not last 7 hours, a rocky planet with an atmosphere it should not be able to keep, a Hubble constant that refuses to resolve, a whole category of early universe objects with no place in the standard model. Webb isn't just finding new things. It's forcing revisions to theories we thought were settled. That is the sentence that matters. Not because it means the science is broken. Science is not broken. It is doing exactly what it is supposed to do, which is update its models when the observations don't match the predictions. But it means that the picture of the universe we had before Webb was incomplete in ways we did not know to expect. And every new image Webb sends back, the Lion Nebula with its dying star cooking its own main from the inside, the Carina Nebula with its hidden nurseries of young stars, the distant galaxies that should not exist at the distances. Webb is finding them. Every one of them is another data point in a dataset that is slowly forcing the most fundamental revision in cosmology in decades. Webb has 4 years behind it, and an operational lifetime of at least another decade. Whatever it has already found that does not fit the models, the next 10 years of data will either deepen the mystery or resolve it. The images it has sent back are extraordinary. What they are telling us about the universe we thought we understood is more extraordinary still. And it is worth remembering what the transcript of Webb's 4 years of operations actually reads, like when you lay the findings side by side. Year 1 brought the deepest infrared images of the universe ever taken, confirmed carbon dioxide in an exoplanet atmosphere for the first time, and revealed the pillars of creation in infrared detail that Hubble's 1995 visible light image could not approach. Year 2 brought the impossible early galaxies and the first biosignature hints at K2-18b. Year 3 brought the Pluto haze discovery, the Lion Nebula, the 7-hour gamma ray burst, and the rocky planet with the atmosphere it should not have. Year 4 is 3 weeks old and has already added a new Carina Nebula image to the archive. Every year has brought something that was not predicted. Not just new objects, but new categories of object. Not just new data, but data that does not fit the existing framework. That pattern is consistent enough now that it is no longer a surprise. It is the expectation. When Webb points at something, the assumption among the researchers working with its data is no longer that it will confirm what the models predict. The assumption is that it will find something the models did not predict. And then the work begins of figuring out why. That is not frightening in the way the word terrifying usually implies, but it is humbling in a way that is harder to process. The universe is older, larger, more structured in its early history, and stranger in its current behavior than 4 years of Webb observations have allowed us to fully explain. Every image that comes back from that gold segmented mirror 1.5 million kilometers from Earth is another reminder of how much of the picture was missing before we had an instrument capable of this. The images are beautiful. They are also warnings. Warnings that the story we told ourselves about how the universe works was always less complete than we believed.